So today, very pleased to have Eunjin Oh from POSTECH. She will talk about her recent work with her student and collaborator, which was accepted to stop this year. Yeah. Please.
Okay, thank you for inviting me. My name is Eunjin Oh, and today I'm going to talk about approximation algorithms for the geometric multimatching problem. Okay, our problem is a variant of the geometric mean cost perfect matching problem. In this problem, we are given 2 point sets S and T in a metric space, and our goal is to compute a minimum cost perfect matching between S and T. And the notion of a perfect matching comes from the graph theory. Here, a perfect matching between S and T is a set of edges between S and T, such that for each point in S, the number of points in T which are mapped with S is exactly 1. That is, the degree of S is exactly 1, and symmetrically for each point in T, the number of points in S which are mapped with S is exactly 1. And the cost is measured by the total edge length in the set. So in this case, this is a perfect matching, and this perfect matching minimizes the total edge length. And in our problem, we introduce a demand function. That is, we are given 2 point sets in a metric space, and each point has a degree demand. Then our goal is to compute a minimum cost multi-matching between S and T. The only difference is that in a multi-matching, we have degree lower bounds. For each point in S, the number of points in T which are mapped with S is at least the degree demand. And the same holds for the points in T. Then, as before, the total cost is measured by the sum of all edge lengths. So in this example, we are given points, red points and blue points, and each point has degree lower bound. Then this is a multi-matching between S and T, and as you can see here, this point has degree 1, and this point has degree 3, and this point has degree 2, which is at least 1. And there exists a very simple 2 approximation algorithm for this problem. For each point in S, find BS nearest vertices in T, and for each point in T, we find BT nearest vertices in S. Then we connect all those pairs like this. For this point, its degree bound is 1, so we connect it with its closest neighbor. And in the case of this blue point, its degree bound is 2, so we choose 2 its closest neighbors. Then this is clearly, this is a feasible solution, but it is not necessarily optimal. For this instance, an optimal solution has a smaller cost. So if these 2 points are sufficiently close, then we can replace those 2 edges with this one. So it is the optimal solution. But using triangle inequality, you can show that this approximate solution is a 2 approximate solution. Okay, this problem, the geometric multimatching problem, has not been treated as an independent topic in theoretical computer science. However, it often emerges as a key subproblem in many applications. Here, the degree bound is necessary for reliability in the design of geometric network geometric network, and it is used as a subroutine for graph-based semi-supervised learning and adaptive anonymization problems. So for those applications, they use heuristics or some other algorithms designed for some more general problem. And a more interesting and more direct application scenario is risk-aware supply chain management. In this application, one point set S represents retail stores, and T represents suppliers. Then we want to diversify the business. This is here B, this demand function can be considered as the diversity demand. So each supplier needs to sell their products to at least BT stores, and each store needs to buy products from at least BS different suppliers. Then this diversity demand allows us to diversify our business, and it helps us to not to lose a significant portion of business if any single store or supplier reduces its orders or it closes. So from this motivation, we worked on the geometric multimatching problem. And there is a graph version of this problem, which is called the B-edge cover problem. The problem is exactly the same as the geometric multimatching problem, but here we are dealing with graphs. It can be a bipartite graph or a general graph. As before, each vertex has a degree bound, and this B-edge cover problem asks to compute a minimum weight edge set such that the number of edges incident to each vertex V is at least B of V. So the degree of V in the solution must be at least B of V. And this problem has been studied before. In particular, there exists n to the 1.5 time exact algorithm, and there is a near linear time approximation algorithm for the B-edge cover problem. And we can reformulate our problem as an instance of the B-edge cover problem. Because we are dealing with a complete bipartite graph on the 2-point sets S and T, and the edge weight is defined as their distance in the metric space. So after constructing a complete bipartite graph in this way, and we can solve the geometric multimatching problem using those algorithms. In this case, the number of edges is quadratic, so this algorithm becomes n cubed time exact algorithm for the geometric version of the problem. And also, we have a quadratic time approximate algorithm for the geometric multimatching problem.
I'm sorry, but for the second complexity, so are you considering the complete graph or the complete bipartite graph?
Which
no,
one?
Sorry, so
This one?
I don't know, so
Here?
the second box. Yeah, yes.
Complete bipartite graph.
Complete bipartite. So if you consider, so the first known algorithms, they are not geometric, right?
Right. And this algorithm deals with a general graph. It's not necessarily bipartite. And if your graph is bipartite, you can get rid of this dependency on alpha.
So what about the geometric complete graph case?
Geometric complete?
Yeah, geometric.
We have a near linear time approximation algorithm for the complete case, but it is very simple, and we wasn't able to find any interesting motivation or application for the problem. And it just combines several known techniques and data structures. And here, the second approximation algorithm is tight because the output size is the total degree bound. And in this talk, we will use B to denote the total degree bound. Then the output size is order of B. But in the worst case, B can be quadratic in the number of points. So if we measure the efficiency of the algorithm, we measure the efficiency of the algorithm using the input size only, then the second one has a tight running time. So our goal is to design an output-sensitive algorithm for the geometric multimatching problem. We want to measure the efficiency of our algorithm in terms of the output size. And this is our main result. For any 2-point sets S and T in a metric space with doubling dimension D of size n, we have near linear time algorithm for the multimatching problem, the general multimatching problem. And if degree bound is just 1, then we can improve the algorithm to take n log n time.
What is doubling dimension?
Doubling dimension. A metric space has doubling dimension D if for any constant r, any ball of radius r can be covered by 2D balls of radius r. So for any ball of radius r, we can cover this ball using a constant number of smaller balls. If this property holds, we say that the doubling dimension of this metric space is D. So the doubling dimension of the Euclidean space, the D-dimensional Euclidean space, is order of D. So our algorithms, both algorithms, works for a D-dimensional space as well. And the second one, this second special case is called a many-to-many matching problem. And the second algorithm improves the best known result of the many-to-many matching problem, which won the best paper award at Sausage last year. And this paper presents an algorithm with n log n time algorithm, but the dependency on epsilon is very large. But in our case, it is polynomial. Okay.
So here epsilon is like approximate, right? So
Oh yes. The approximation factor is 1 plus epsilon. Okay, our approach is totally different from this Sausage paper. This Sausage paper doesn't use some known algorithms from graph theory. But in our case, our main approach is to use the connection between the multimatching problem and the B as cover problem. More specifically, we implement the algorithm for the B as cover problem using some new geometric ideas as using some basic geometric data structures. So we start with this near linear time algorithm by Huang and Petit. And this algorithm indeed deals with the F matching problem. It is a complementary version of the B as cover problem. So in the F B edge cover problem, we have degree lower bound, and we want to minimize the total weight. On the other hand, in the F matching problem, we are given a graph and we are given a degree demand, but here we want to compute the maximum weight edge set, and we have a degree upper bound. So using a simple argument, you can show that if C is a B edge cover of the graph, then the complement of C is an F matching. Here F should be set as follows. Fv is the degree of V minus So this shows that if you want to design an exact algorithm for the B matching problem or the F matching problem, the two problems are equivalent. If you have an algorithm for the B edge cover problem, you can use it to design maximum weight F matching problem, and vice versa. However, we want to design an approximate algorithm. But in general, this reduction doesn't work for approximation algorithms.
But you're also output sensitive, no? And
In
this changes.
in this case, the running time is order of n,
Okay.
which is linear in the input size. So the graph problem, the input size is m plus n, and this algorithm is linear in the input size, so we can't improve this algorithm even further. However, in our case, the input size is n, the number of points. However, the number of edges, which is defined implicitly, is quadratic. So if we apply this algorithm to the geometric multimatching problem, we can get a correct algorithm, but the running time is not sufficiently good. So this algorithm, for approximation algorithms, this reduction doesn't work in general. But if we introduce a dual and approximate complementary slackness condition, then this reduction still works. That is, imagine that you have a F matching M, and you also have its corresponding dual. And M and G, this dual, satisfy this approximate complementary slackness condition, then you can use this matching to obtain an approximate B edge cover.
So what is approximate complementary slackness condition?
Its definition is quite complicated, but it is not important. Purpose. So the important thing is that if you have a matching and if you have a dual, and if they satisfy a certain condition, then the reduction works. So their goal is to design an algorithm for computing a matching and a dual satisfying this condition. Then this algorithm can be used to design an approximate B edge cover, approximate algorithm for the B edge cover problem. And so now we focus on the F matching problem. And this algorithm consists of several scales. Here W is the maximum edge weight. It consists of log W plus 1 scales, And at the beginning of each scale, we start with the empty matching. And the dual comes from the previous iteration, previous scale. And then we set this error parameter at the beginning of the scale, and we set this approximate edge weight.
So weight was the distance in,
Yes,
in your problem?
Here we are dealing with a graph problem,
Oh, graph
so
problem.
it is
Okay.
edge weight. And in each scale, we repeatedly find an augmenting path, and then we update the current matching using this augmenting path. And this augmenting path consists of eligible edges. It is, again, not very important, but I should mention that this eligibility depends on the dual values of its endpoints and the approximate weight. Then G eligible is the subgraph of G induced by eligible edges.
Sorry, but what is the intuitive meaning of this ZI?
ZI,
Yeah, Z. So,
you can state this problem as an LP problem,
yes.
and there is a dual
Uh-huh.
LP.
Yeah. So that is the variable in U.
Yeah, yes, right.
So it's a cover, right? The vertex
Yes,
cover.
yes,
vertex
yes.
cover. Yes.
That's why it's a weight on vertices, right?
And-
The GV.
And indeed, this approximate slackness condition also comes from this LP dual
Mm-hmm.
LP. And in each scale, we run this algorithm order of 1 over epsilon times. In each iteration, we find a maximal set of edge disjoint, augmenting paths, and alternating cycles, such that after removing those edges from the eligible graph, this eligible graph doesn't contain any augmenting paths. And then we update this matching using those augmenting paths and alternating cycles. Then at the end of step 1, we don't have any augmenting path, so we modify the dual values to produce more eligible edges. So by repeating step 1 and step 2 order of 1 over epsilon times, we can complete each scale. And one important thing is that this algorithm uses a single DFS tile search on the eligible graph. And we repeat this procedure log W times order of 1 over epsilon times. So the running time is dominated by this number of runs of the DFS tile search. And in our case, the geometric version of this problem, we want to implement this algorithm efficiently in the geometric setting. So our main goal is to implement this DF style search in our geometric setting. But here we have two efficiency issues. As I mentioned earlier, the correctness immediately follows from the scaling algorithm, but the running time is quadratic, and we need the running time linear time approximation algorithm. first issue is that the graph itself is quadratic. Although the input size is n, because we are dealing with a complete bipartite graph, the number of edges is quadratic. But the first issue can be handled using some known technique. We first slightly perturb the point set, and then we use well separate pair decomposition. I will talk about this in more detail later. And these two tools are also used in many geometric matching problems. And they sparsify our graph. Then we can, using this data structure, we can construct a DFS tree on the eligible trees in near linear time. So a single DF search can be done in near linear time. However, in our case, our goal is to compute on a set of edge disjoint augmented path and alternating side point. Because in our case, this is one point, and it might be incident to many edges, many matching edges. Those edges are in M, and those edges are not in N. And it is possible that one augmenting path intersects this center, and the second one intersects the second one. So the number of augmenting paths containing a single vertex can be f of v. So we need to visit the same vertex multiple times. So the first, this is sufficient for our purpose. That is the second. This issue is closely related to the second issue I described here. The structural change to M can be quadratic. At the beginning of each scale, we start with the empty set. But at the end of each scale, M becomes an approximate F match. So its size is m squared minus b. So even if b is very small, the size of m can be very large. And in each tutorial, we update m until it becomes an approximate F matching. So the structural change to M can be quadratic. And moreover, it is to store, to represent M, we need quadratic space. So our solution is to represent M implicitly using order B space. And then we design an algorithm to update M in total order of B time. Okay, now I'm going to talk about a brief sketch of our algorithm. As a pre-processing, we perturb points in the input set so that the spread of the resulting set becomes a polynomial in N. So here spread is the ratio between the diameter and the distance, minimum distance between 2 points in the ratio between the longest edge length and the shortest edge length. Then if it becomes order of it becomes polynomial in n, then W becomes a value polynomial in n. Then this becomes log n. So now we have log n scales, and we have over epsilon iterations. And then we construct a well-separated pair decomposition of the point set to define adjusted weights. So here, well-separated pair decomposition is defined as follows. First of all, two point set x and y is said to be C separated if the distance between x and y is at least C times the diameter the diameter of dx and the diameter of y. And a well-separated pair decomposition of two point sets is a set of well-separated pairs. So each SI, TI is well-separated, and for any 2 points, one from S and one from T, there exists a unique pair that covers A and B. And it is known that for any constant C, there exists a C well-separated pair decomposition consisting of a linear number of pairs if the doubling dimension of this metric space is a constant.
Is this like somebody's theorem or?
Sorry?
So is this by
It is a
known?
known result, a very well-known result.
Okay. Never.
It is also covered in some computational geometry textbook.
Uh-huh. I see.
But what is dependency on doubling dimension? Very hard.
2 to the order of d times n. Okay, then using well-separated pair decomposition, we can define this adjusted weight. That is, for any point pair from the input point sets, we let their adjusted weight as the distance between SI and TI. And because there exists a unique pair covering this point set, this weight is well defined. And using this, we can handle each pair separately. Or a single pair, we have many points here. Then the distance between any point in S and any point in T is the same. So we can update M in a batch way. This is our main idea. Yes. Okay, so now we are going to deal with each pair, each point pair, or each pair of point sets separately. So we have SI and TI. So at some point of the search, we reach some point in SI. And at this point, we want to find some eligible edge connecting this point to some point in TI. And because the eligibility depends on the dual of one point and dual of the other point, and their weight function. And in this case, it is constant. And because we have fixed the starting point S, the eligibility depends only on the dual value of the points in Ti. So we use some binary search tree on the dual values of the points in Ti. And using this, we can find an eligible edge connecting S and some point in Ti efficiently. However, as I mentioned earlier, the size of M can be quadratic. Okay, at the beginning of the algorithm, M is the empty set. So there is no edge in M between Si and Ti. So we can store M explicitly at the beginning of the algorithm, beginning of each scale. And at the end of the algorithm, the complexity of M is n squared minus b. So in this case, we can store the complement of M explicitly, because the complement of M has size order of b. However, in the middle of the algorithm, both M and its complement might have quadratic size. So we can't store neither M nor E minus M in the desired time. And to implement the graph algorithm, we need to represent M using order B space. And our approach is to mix these two approaches. We have point set X, a point set Si, and point set Ti. We want to represent a set of edges in M between Si and Ti. And for this purpose, we split each set into a constant number of subsets. So this is X1, X2, Xr. And we split Ti in the same way. And for one subset pair, we represent edges in M between Xi and Yj, using storing M explicitly. And for some other pair, we represent edges in M between, what I can say, Xi prime and Yj prime. We store its complement explicitly. No.
Good.
Okay, we subdivide Si into a constant number of subsets, and also we subdivide Ti into a constant number of subsets. And to represent the edges in the matching between one subset and another subset, we use one of the two approaches. We store M explicitly, or we store the complement explicitly. So in this way, we can fully describe M for all all pairs of point sets. However, this does not ensure that the complex of the representation is order of B. For any matching, we can use this strategy, but the size of the representation depends on the so we cannot ensure that the size of this representation is order of B. So to ensure that the size of this representation is order of B, we need to slightly modify the graph algorithm. To avoid this, we use batch update operation. At the beginning of each scale, we look at each pair of point sets, and we include all augmenting paths of length 1 in a batch way. There can be many, more than order of B augmenting paths of length 1, but we show that we show that we can those augmenting paths can be described in an explicit way. That is, given a pair of point sets in the relative characteristic position, and a subset of the edges between xi, this is xi, x prime, and this is y prime. And we can insert all edges between xi and x prime and y prime, excluding the edges of e prime, simultaneously, efficiently. That is, for all of, so if we want to, the set of all augment paths of length 1 can be partitioned into a constant number of subsets, such that each set is the complement of this edge set, the complement of this augmenting path in this complete graph has size order of B. What is it? As I mentioned earlier, we want to use this approach, but it is not clear how to define those subsets. And also, even if we can represent our matching in this way, it does not guarantee that the complexity of the representation is order of B. For this purpose, we use batch update. At the beginning of each scale, so our goal is to find all augmenting paths in the eligible graph, but we split this procedure into two parts. In the first part, we update all augmenting paths of length 1. Once it is done, in the second part, it is sufficient to, in the second part, the total complexity of the remaining augmenting path is order of B. It consists of two parts. So in the first part, we augment all augmenting paths of length 1. And in the second part, we compute the remaining augmenting paths. The complexity of the augmenting path in the second part is order of B. This is what we proved in our paper. And the high complexity comes from the first part. And for the first part, we don't need to compute all augmenting paths explicitly because they have a certain structure. So we can update the matching in the first part using implicit update. That is, we just specify for each point pair, a pair of point sets, we specify the edges not contained in the augmenting path. So their structure is very dense, so their complement has their complement in prime head size. So for first part, we use the second approach, and for the second part, we use the first approach. So by combining two approaches, we can represent M using order of B space, and moreover, we can update M in time linear in B. And this is the overall structure of our algorithm. And finally, we was able to obtain a near linear time approximation algorithm for the geometric arithmetic problem. Okay, thank you for this. Oh. Thank you for listening.
Thank you. Any questions?
This is a super ideal, well-separated pairs, or how did you call it?
Well-separated pair decomposition.
Well-separated pair decomposition. Like, do you have a similar kind of tool for graph classes, not necessarily geometric graphs, or do you think there is a chance that we can get something like that?
Yes, for unit disk graphs. So unit disk graph is.
You can use Blackboard. Yeah.
Oh yes. Is a graph class defined by a set of unit disks. Here, each disk defines a vertex of the graph, and we connect two vertices if their corresponding disks intersect. In a unit disk graph, there exists well-separated pair decomposition consisting of order of n pairs. And this is the only graph class that, as far as I know, this is the only graph class that has well-separated pair decomposition.
So meaning for any constant C, you can.
Yes. And here, this constant depends on C.
So can you define the well-separated pair decomposition for triple of points?
Triple point set. Then how can you define?
Yeah, so like I'm not sure that how it will be applied, but so if there is a point at STU, and yeah, so STU is well separated if S is somewhere in here and T is somewhere in here and U is somewhere in here. Right, so they have a sufficient distance between each other and kind of separated by some band or yeah, and then yeah. So is there something that kind of notion in computation geometry or the computation problem?
I don't know if there exists an explicit result. In fact, this well-separated pair decomposition, the original well-separated pair decomposition, deals with a single set. But in our case, we are dealing with a bipartite case, so we slightly modify the original notion of well-separated pair decomposition to handle a bipartite case. But so I think that it's possible to extend this notion to deal with a triple case, but I'm not sure at this moment.
So,
About the eligible edges,
Yes.
it is formulated by the LP duality,
Yes.
like that. So while during the algorithm, do those values have fractional values?
No, they are integers. The motivation of these dual values come from LP duality. However, it originally comes from LP duality, but later it was modified and modified by many different papers. And so in this paper, Huang and Petty, the dual values are always integers. And moreover, in this case, edge lengths are integers. Yes, I think this is why they restrict dual values to integers.
But probably the matrix that it defines will be totally modular, so this particular linear program will always have integers optimum solution. Probably.
Oh yes, right.
Yeah, so-
Right.
Because it's coming from bipartite graph. How fast? So you said there exists a well separated pair decomposition, but you didn't. But don't you need an algorithm to generate?
Yes, there exists a linear time algorithm for
Linear time
constructing
algorithm.
a well separated decomposition.
And also, are there some other instances where? So this is like, I mean, for me, we already know like polynomial time algorithm for matching or discover, but your algorithm is like speed up, right?
Yes.
Are there other instances of the geometric problems where this kind of problem could be meaningful? Like, do you have some open problems where we could think about?
Yes. In fact, our original problem was this. We are given a set of papers, submissions, and we are given a set of reviewers. So we want to assign papers to reviewers, but this is a very simple paper. So this paper requires only 2 reviewers. So we need at least 2 reviewers. And for this paper, we need 3 reviewers and so on. And for this part, this reviewer said that he or she wants to review at most 3 papers. So in this scenario, for this part, we have a degree lower bound, and here we have degree upper bound. And we want to find a set of edges satisfying these two constraints, and among all such edge sets, we want to find one that minimizes the total cost.
But in the geometric setting or in
In
abstract?
geometric setting, they are point sets.
I guess there's a polytime algorithm, right?
Yes.
But-
There
but,
exists a
uh,
polynomial time algorithm. In the graph version of this problem,
Yeah.
we can solve.
By the same logic, maybe just reduce.
We can't use the same.
Because on one side you can change lower bound to upper bound, and reduce F matching.
In this algorithm by Huang and Patty, they use this reduction. And after reducing the problem into the F matching problem, we have a feasible solution, a clear feasible solution, which is the empty set. In the case of the F matching problem, empty set is a feasible solution. But in this case, we don't know any feasible solution.
I see. Okay, any other questions?
So I have one more question. So is there any hypergraph version for your problem?
Hypergraph.
Yeah, 3 uniform, and so you want to
Higher
find,
dimension.
you want to find some triangle which has a minimal cost or something.
There are many variants of the geometric matching problem, but I haven't seen any geometric hypergraph, the graph version of the hypergraph matching problem.
Maybe try to minimize the areas of the triangle. Alright, any other questions? So if not, let's thank the speaker.